Hello, and welcome to Business Calculus, L'Hopital's rule for 0 divided by 0 form. In our previous discussion of limits, we had some cases that were called indeterminate forms. For example, if we have a limit where the limit as x approaches c of f of x divided by g of x, and the limit of the numerator and the limit of the denominator are both equal to 0 as x approaches c, we call this a 0 divided by 0 indeterminate form. In our previous examples, we had to do some algebraic simplification in order to find the limit, but L'Hopital's rule is a powerful new tool that helps us evaluate the limit in these cases. Let's look at an example that we had previously that we solved algebraically to get ourselves warmed up. Here we have the limit as x approaches 2 of x squared minus 4 divided by x minus 2. Now, the numerator and denominator are both polynomials, which means that we can just plug in the value in order to evaluate the limit. Plugging in 2, we see that the numerator is equal to 0 because we have 4 squared, or 2 squared equals 4 minus 4, and 2 minus 2 in the denominator, which is 0. This means we have some more work to do. And if we perform some calculations, namely factoring the numerator and canceling the like terms, we see that this expression simplifies to the limit as x approaches 2 of x plus 2, which is a polynomial that we can evaluate, and we get that the limit is 4. Now let's look at L'Hopital's rule. It's pretty simple, but satisfying the condition is very important. For a real number c, if the limit as x approaches c of f of x equals 0, and the limit as x approaches c of g of x is equal to 0, then the limit of the quotient f divided by g is equal to the limit of the derivative of the numerator divided by the derivative of the denominator, if the second limit exists or is equal to plus or minus infinity. Now, this is incredibly powerful because when we take derivatives of functions, in particular if they're polynomials, they tend to get simpler because the power rule reduces the powers of the terms in the polynomial. So taking a derivative makes it a lot easier to look at. However, we note that this is extremely dangerous. We have to make sure, whenever we use L'Hopital's rule, that we have a 0 divided by 0 form before we apply the property. It's easy to get lazy and think that this allows you to evaluate any type of limit that comes in the form of a quotient, and that's not true. You must have an indeterminate form before you're allowed to use this rule, so be careful. Now we're going to look at some examples here. And we're going to start off by following the most important part of L'Hopital's rule, and that is to make sure that we are in a 0 divided by 0 form before we get started. So looking at number 1, if we evaluate the limit, and I'm going to do that in blue representing scratch work, if we plug in 2, we get 2 squared minus 4 divided by 2 minus 2, which is something that looks like 0 divided by 0. So this means that L'Hopital's rule applies in this case. So we say that this limit is equal to the limit as x approaches 2 of the derivative of the numerator, which is just 2x, divided by the derivative of the denominator, which is 1. Which is an extremely simple limit to evaluate. We just plug in 2. Of course, this divided by 1 is just 1, and we get that the answer is 4, just like we had in our previous case. All right. For number 2, again, we want to plug in 1 to see that this is indeed an indeterminate form. So we replace x with 1. We have e to the first power, which is just e minus e, which is 0, and then 1 minus 1, which is 0, and I'm using the squiggly equal sign to signify that we have 0 divided by 0, but of course we know that this is undefined. It doesn't make sense So it's bad notation, but it's useful for the purposes of demonstration here. Next up, we know we can apply L'Hopital's rule, so we're going to take the derivative of the numerator and the derivative of the denominator. So the derivative of the numerator is just e to the x, because the e is a constant, and the derivative of e to the x is itself, and the derivative of x is 1. So we have the limit as x approaches 1 of e to the x over 1, and this is a continuous function, so we can just plug in the value of the limit, and we see that the limit is equal to e. Lastly, we're going to check this case here. We're going to plug 1 into both parts of our function here. And we see again that we get 0 divided by 0, because the natural log of 1 is 0, and 1 minus 1 to any power is going to be 0. So we can apply L'Hopital's rule, and it's going to look a little bit more complicated because we're taking the derivative of a logarithm. So the derivative of the natural log of x is 1 over x, and the derivative of the denominator is going to be 3x minus 1 squared times the derivative of the inside, which is 1, using the chain rule. And simplifying this, we're going to get 1 over 3x times x minus 1 squared. Now, I'm going to point out the fact that I made a very small but important mistake. I did not copy down the limit notation when I made this step. You must copy down this limit notation in each step when you're applying L'Hopital's rule, because you're not saying that the arguments of the limits are the same. You're saying that the actual value of the limit is equal in each of these cases. So it is extremely important, even though it is cumbersome, to write down the limit denotation on each step until the final step when we evaluate the limit. All right. Now, looking at what we have written down here for our last limit, we see that I have 1 over 3x times x minus 1 quantity squared. Now, the limit of 1 over 3x is very simple. It's just 1/3, because I can plug in 1 to that. But on the right-hand side, we have 1 over x minus 1 quantity squared. And this limit is going to behave like the limits we had from the previous video, where it goes as 1 over x to some even power. And because of that, we're going to have the limit in this case is going to be equal to infinity, because the limit of 1 over x squared as x approaches 0 is infinity. All right. Here we have an example of a scenario where L'Hopital's rule may not apply. So what we're going to do is we're going to check by plugging in 1 to the numerator and denominator to see if L'Hopital's rule gives us what we want. And we see that the numerator is equal to 0 and the denominator is equal to 1 if I plug in x equals 1. Okay? Now, this should make it very clear to everyone that the answer to this problem is just going to be 0, because I was able to evaluate the limit straight away by just plugging in the number. But if we weren't paying attention, we could have decided that we were going to apply L'Hopital's rule to this problem. If I had done that, we would have gotten that the limit as x approaches 1 is 1, which is incorrect. So the lesson here is to make sure that L'Hopital's rule is applicable. So you can only use it in cases where you satisfy the 0 divided by 0 property. So be very careful. Lastly, we have a very special case of L'Hopital's rule, a situation where we need to apply it multiple times to evaluate our limit. So we have the limit as x approaches 0 of x squared divided by e to the x minus 1 minus x. Now, what we're going to do is check to make sure that L'Hopital's rule is satisfied. We're going to do that in blue. We get e to the 0 minus 1 minus 0. And we see that we have 0 divided by 1 minus 1 minus 0, which is indeed 0 divided by 0. So that allows us to apply L'Hopital's rule. We take the limit as x approaches 0. In the numerator, we just have the derivative being equal to 2x. And then in the denominator, we have e to the x minus 1, which is the derivative of the denominator. Okay? This doesn't look like something that we know the answer to, but it does look simpler than the problem that we had. So we are going to, again, plug in 0 to see if we have a 0 divided by 0 indeterminate form. And it turns out that we do. So we get to apply L'Hopital's rule a second time to this example. So again, we take the limit as x approaches 0. We take the derivative of the numerator and the derivative of the denominator. And we finally have something that looks like a limit that we can evaluate. Of note, this is no longer an indeterminate form. If I plug in 0, which is how we evaluate the limit, we notice that I'm not going to get 0 divided by 0 anymore. So we plug in 0 to evaluate the limit at this point, and we get 2 divided by 1, and we see that the value of the limit is equal to 2. All right. So for these types of problems, make sure at each step it satisfies the indeterminate form condition before you use L'Hopital's rule more than once. All right, what I would like for you to do now is to find the following limit using L'Hopital's rule. We have the limit as x approaches 0 of the natural log of 1 plus x squared divided by x to the 4th power. Here are the choices for your answer. Infinity, 0, negative infinity, or none of these. Thank you very much for your time.